My first speaker is Brad Spires. He's Principal Solution Architect at Micron. Brad joined Micron after 20 years on Wall Street, where he applied some very advanced computing technologies such as GPU cards to solve business problems such as Monte Carlo simulations. He now works with Micron clients solving problems like cloud computing, high-performance computing, big data, and machine learning. So he'll be speaking to us about seamless prediction at the edge using TensorFlow and FPGAs. So welcome, Brad. Okay.
So thanks, Mike. So seamless prediction at the edge, right? TensorFlow, FPGAs, there's a lot in the title, right? So I just want to check in a little bit, right? So who here deals in the edge? Who works in the edge, right? Deploys things on the edge, okay? Who here deals in TensorFlow? Okay, we got a few, all right. Who here has no clue what TensorFlow is? It's okay, it's all right. And who's other, right? Who's not quite either category. It's all right. Okay, that's cool. All right, how about accelerators? Who here deals in accelerators? Okay. Who here deals in FPGAs specifically as accelerators? Who here does not deal in FPGAs or accelerators? Okay. So where I'm heading with this, right, is that this is a combination of technologies, right, that address particular challenges that we find at the edge, right? So what we're seeing is that the edge gives us some new things to start to take a look at, right? So as you start to think about solutions at the edge, right, what becomes apparent very quickly is you face a lot of limits, right? So I think pretty intuitively, you have limits in terms of weight, power, and space. And what that really means is you can't move the data, right? You cannot possibly have enough bandwidth to move the data back to a cloud, right? Do some computation and return it back. And beyond that, you need capabilities. I mean, I think we've heard of some of the autonomous car incidents recently, right? You want to make predictions quickly. So the question, quickly comes up, okay, how do I deal with this, right? How do I create sort of a capability at the edge where I cannot move this data, and how do I choose an architecture to do that, right? So as you take a look at that, you say, no, wait a minute, like low power, right? Many of us start to think about FPGAs, right? They've got the power, they've got the speed, right? But the challenge is, and I did this myself, has anyone actually tried to create a project for FPGAs? Okay. So when I did this, right, with machine learning at a startup after I left the banks, so I came in and I said, okay, here's our network, here's what we're going to do, right? And he said, wow, that's really great, right? Very sophisticated. And they came back and they said, here's the price, and it'll take 6 to 9 months. I said, no, wait a minute. I have data scientists, right, that are working nonstop, right? And we make changes every day, right? DevOps, like right now, like all the time. And they said, well, that's fine, no problem. So for every change you make, right, just simply file a change request with us, right, and we'll extend the project a little bit more, right? It'll cost a little bit more and take a little more time. I said, 6 to 9 months. I said, there's just no way it's possible. We cannot make this work as a system. So what I'm about to do is I'm about to review a couple of the elements here, okay? I'm going to tell you about some work we're doing with partners right now, right, about how we can create a capability using FPGAs without facing that same challenge, that same gulf, right, that 6 to 9 months of time it took in order to create the capability. So just to make sure we're all on the same page, right, we're talking about field programmable gate arrays. That's what an FPGA is. Right? It's different from a CPU in that it doesn't have an instruction set architecture, right? It doesn't have a predefined set of things. that we're doing at the same time, right? And it's dynamically reprogrammable. So what that means is I can update it like all the time, right? And the intuitive thing I think you want to walk away with is, and this picture is trying to show this, on the right-hand side you have the FPGA. And the thing you want to think about intuitively is it has much more parallelism. And so the question is, right, how can I easily program or expose that capability, right? Because that's what's different from CPUs. Now at the same time, right, this is different from other accelerators, such as GPUs. And it's different in the following way, because many of us might say, no, wait a minute, right, Brad? There's another architecture here. GPUs, right, also have an immense amount of parallelism available. But the difference is, right, that FPGAs are designed to handle sparse data, like we would see at the edge, and also batch sizes of 1, right? So when you're at the edge, right, and you get some data in, you want to respond immediately, and you don't have the luxury of waiting until you have a larger batch. So now let's pull back a little bit, okay? Let's start to talk about what are the challenges that customers face, right? Almost like what capabilities would you want to be able to create with such a combination? Well, we clearly want to understand, you know, essentially our environment, right? People or faces, like if you saw our display last night. Body poses now, right? Fingerprints. And even time series. So the thing that, for those of you who might be more familiar with networks, there's really 2 types of challenges here, right? There's either recognizing something, which is typically done with a convolutional neural network or a CNN. And then there's also time-based recognition, right, or time-based patterns, which are normally handled with a recurrent neural network. And the current flavor of the day is LSTMs, long short time models. So now we're going to dive into performance, right? Let's get down to the numbers, okay? What can I do, how much can I do, and in what power envelope, all right? So what we're talking about here are, this will scale down to 24-watt modules. So what you see on the right is a combination of an FPGA, right, a high bandwidth memory part called a hybrid memory cube, right, and what that's able to produce is 191 gigaops per second, using 60 gigabytes per second of memory bandwidth, and again in a 24-watt envelope. So these solutions or capabilities, what this could do is this could deploy certain networks for you and process a stream of data. Now, there's 4 columns here, right? So I've been reading from essentially the left-hand column. The way to think about this is a scalable solution. You can actually start small, and depending upon the power envelope that you have at your edge, you can start to scale up to actually look for more things within your signals. So you can start to, say, look for not just recognizing a face, right, but recognizing cars or bicycles, right? Deploy multiple networks, time-based signals as well. All within the same, as the stream flows through, you can actually flow it through multiple modules, multiple FPGA modules, and then do detection of multiple types of models at essentially the same time. So how do we do this, right? We talked about there's this gulf, right? You know, help me out here, Brad, right? I'm still stuck in the 6 to 9 months you were talking about to deploy this, right? How do I get over that hurdle, right? So now we have the physical pieces, right? We have the physical components, right? 191 gigaops a second. But now help me through the programming piece. So we talked to a partner, Forward Next, okay? And Forward Next came to us and said, we have this compiler, right? What you can do is you can literally write your model, right? Get the output of the model, train it just like you do, right? So your data scientists are going to use, you know, Python, right? They're going to use TensorFlow, Caffe, PyTorch, right? Output the model, and they can deploy it automatically. And they said, not only that, like, there's this second thing we're going to give you, right? We're going to give you a super efficient deployment capability, right? If we were to look at doing this model and performing this model on the edge, where power is at such a premium, right? What we want is as close to theoretical perfection as we can possibly get, right? So if we were to look at theoretical perfection, right, that'd be a measurement of 100%, okay? Forward Next has documented they're able to get between 91 and 94% of that perfection on things like AlexNet, standard challenges in terms of prediction. Now, how do they do that, right? This is a really hard problem. And the answer is in the way they fetch data. So typically, when you look at these networks, right, we're all here, right, talking about these deep neural networks, AIs, right? So what's happening to these networks, right? The simple, few layer networks are turning into hundreds or thousands of layers. So what used to happen, right, the naive approach, so this table here on the lower right, what this is going to show you is two basic approaches, right? On the left-hand side of the table, it's the naive approach, right? And essentially what people used to do is they would fetch literally down like one level or one column, if you want to think of it that way, in your network, right? And there's hundreds to thousands of these, right? But when you did that, right, that naive approach, it essentially fetched a small matrix. Now, Forward Next took a completely different approach. They said, you know what, we're going to go out and fetch an entire, what they call a trace. It literally is, if you think of like left to right, all the way across the network, I'm going to fetch almost 100 times as much data in one go. And that gives you what you might think if you've been in this area for a while, right? In the GPU days, we used to talk about that as arithmetic intensity, right? So you could actually, as long as you had enough arithmetic intensity, you could easily use like a GPU for that. They're taking a very similar approach right here, in that they're, by fetching 100 times as much data, I suddenly have a lot of things I can now work on. And while I'm doing that work, I can hide the things I don't care about, right? The fetching of data. I don't want to sit around and wait for fetching things from memory. I want to compute all the time and be efficient. And traces, fetching these long traces, let us do that. So now once I have the trace, right, how do I actually run that? And that's where we have the hierarchy from Forward Next. So in terms of what we lay out on the FPGA, what you're seeing here is the hierarchy in terms of the large traces at the very top, fetched in green, right? Followed by the compute unit sections here in the compute clusters, where they have the data distribution networks, right, down to essentially the ALUs and how they do some of the multiply accumulates. But again, right, this all comes from fetching very long traces, and that enables this design. So now you say, okay, we've essentially turned, right, what used to be a latency-bound problem into a bandwidth-bound problem. That's essentially what's happened. So now the key to the design turns into, how do I have efficient memory bandwidth? And here you could consider the Micron hybrid memory cube, which has 8.5 times the bandwidth of DDR4. But the difference is you actually use less power. You only use 30% of the power of DDR4 to use a hybrid memory cube. I've had a number of people say, how is that possible? Right? Well, what we did is we used through silicon vias, right? So this is a three-dimensional, right, package, right? And what happens is that we actually divide them up. And you can think of like a little bank, a vertical bank, like a little column, right? A little slice of this DRAM layer. And we light up only that little vertical bank at one time. That's how we're fetching this data. And that's what gives us this power efficiency. So, okay, so back to how do I actually do this? Let's walk this through again just to make sure, right? So if I had to ask people to write the Verilog and the HDL, right, or VHDL, it certainly turned into months of delay, right? But now again, right, we can go back. You can take your network. So the network that is optimized or specific for your problem, right, and that's up to you. You can go ahead and create that. Your data scientist can create that in Python, right, without any knowledge that there's an FPGA involved at all, right? Now they output that network description, right, and the network description is what is ingested by the Snowflake compiler, and then seamlessly, literally running a shell script is what deploys it to an FPGA versus other architectures. So to someone deploying or using this sort of collection of tools, right, they're able to take advantage of FPGAs, TensorFlow, or PyTorch on the edge, right, with essentially no knowledge. The compiler does the heavy lifting for you. And doing that, right, you can deploy capabilities such as, in this case, facial recognition. So then immediately we start to get the questions, well, wait a minute, right, what models do you support? What frameworks? And the answer, the thing I want you to walk away with is remembering this handles any model, any framework. Now, the very next question is people say, now, wait a minute, right? I need to be able to make sure that the numbers coming in off my sensors, right, that you can handle the dynamic range that we have, right? So we want to be very clear and open, right? This is a working, functioning system, right? This isn't something on a chalkboard, right? So we use 16 bits precision, right? We use 5-bit integers and 11-bit fractions. We get so many questions about this, right, that we are considering going to a 16-bit floating point representation just to make sure that people are more comfortable, right? But again, we are using a few more bits in some places just to make sure that the overall system is functioning correctly or as you would expect. Now, just to go through this one last time, right, in terms of steps to deploying models on FPGAs, right, we really are trying to make it as simple as a compiler can do heavy lifting, right? So your data scientists define these models in PyTorch, Caffe, or TensorFlow, just like they're used to today. No code change, 0, right? You ingest your data, and you can use the cloud, right? You can do it anywhere you want in terms of training your model. If you have a GPU farm, however that works for you, right? Then again, right, the output of that is always just the trained model definition or the network definition, right? And that's what the Snowflake compiler ingests and again deploys on an FPGA. So now that we have this, right, you start to say, well, this is really interesting, Brad. You've shown these pictures of 24 watts, right? But clients started to call us up and ask for different things. So we had this capability, and clients called up and said, that's really cool, but I have a slightly different problem. Can you help me out? So clients called up in areas like medical imaging. They said, hey, look, the dynamic range or the fidelity of the sensors that we have now in the medical area is just exploding, right? And the challenge that we have is we can't fit our models in memory, right? I can't run it. I can't use the accelerators. I just can't do it. Is there anything you could do? You're a memory company, right? Could you help me out? So we created this card you're seeing here on the right-hand side, all right? It's got, in this case, up to 512 gigabytes of memory. So what we're doing is we're combining like a capacity memory, like a DDR4, with the high bandwidth memory to give some of the advantages I talked about, right? So you see the hybrid memory cube there on the lower right. And again, right, we can use different types of FPGAs. Actually, I've talked about Xilinx you've seen so far in some of the pictures, right? But we actually support both Xilinx and Altera/Intel. We can do either one. So what this does is this allows you to handle larger problems. So for a number of different areas that we're seeing on the edge, right? If you're doing oil exploration and you're pulling sensors behind your boat, right? We see people doing a lot of video analysis, right? Or let's say some government forward deployed assets or things of that nature. We have seen a very large interest in this sort of approach that allows you to handle things that are larger than some other accelerators that might stop out at 6 or 12 gigabytes of available memory. So in summary, right, what we've talked about is that the edge brings up a new set of challenges, right? That it creates harsh limits, really, on power as well as bandwidth. And what that implies is you need to do the computation there at the edge. We can't move it to some other place, such as the cloud. And that in the past, a number of people have seen that FPGAs are a great match. They're a great match for power. They're a great match for sparsity. They're a great match for handling batch sizes of 1. The challenge had always been that it took far too long to program, right? It took months when, in fact, the workflows around how we develop data science, it's gone DevOps, right? You want to do it the same day, the same hour, the same minute. And the good answer is you can do that now. So using the forward next Snowflake compiler, you can deploy any framework, any model, right, onto an FPGA with no coding. At the same time, right, we've finally seen that using these techniques, we can also support larger problems with boards with up to 512 gigabytes of memory. Thank you.